Hello, my math friends. This is Mrs. Schlecht, and in this video, we're going to go over exponents. All right, you know that there's a few materials you need in order to be successful with this activity. First, you're going to need your Envision textbook with our little robot friend on the front. Second, you're going to need your math notebook to take those amazing notes. Third, you're going to need a pencil. And fourth, last but never ever least, that positive math attitude. Like real talk moments, my friends, okay? First, this video goes with lesson 3-1 in your Envision book, and you can find the key concepts page on page 126. Now, exponents is something that you may have talked about in 5th grade, so some of this might be review. However, since we all know that our 5th grade year kind of had a rocky ending, right? Some of this might not be so familiar to you, all right? So because of that, we're not only going to talk about exponents, but I want to kind of backtrack a little bit to talk about factor trees, all right? And that kind of goes with like our fact families and things like that. So what we're first going to look at, my friends, is the example that's in that key concept box. Again, page 126, but we're going to kind of work backwards and kind of work through it a few different ways, all right? So let's get started. Again, we are going to look at that example that's on the key concepts page on page 126, right? But we're going to kind of make it work for us. So here's where we're going to start. We're going to start with this number 625. Okay, my friends? And I know, and you know, that there are different numbers we can multiply together in order to get this big old number of 625. Now, if you don't really know all the different factors that we can multiply together to get this number, that's okay. But I want you to take a peek at just one special number really quick, okay? This last number right here is a 5, my friends, a 5. Now, when we have a number that ends in a 5 or a 0, we know that 5 is a factor of it, right? So for my factor tree, I'm first going to put 5 as one of my factors, but then I need to think, 5 times what will give me 625? Hey, check it out. So we know that if I do 125 times 5, that gives me 625. Now let's think, my friends. So I know that the number 5, the only way I can multiply and get 5 as an answer is if I do 1 times 5, right? That means that it's a prime number. Prime numbers, which we'll talk about more in another video, my friends. Prime numbers are those numbers that the only way in the world you are able to multiply in order to get them is when you do 1 times itself. So 3, that's prime. 2, that's prime. 11, that's prime, right? And 5 is also a prime number. So when we're doing these prime factorization trees or factor trees, when I get a prime number, I want to circle it because I'm done. I'm done breaking that number down, okay? So this tells me again, it's prime. 5 is prime, I'm done working with it. However, my friends, check out this number right here, 125. That is something we call composite, a composite number. And what that means is that there are so many other numbers inside of here that I can multiply together to get 125. So let's keep thinking about it like this, my friends. I notice, oh my gosh, again, there's a 5 at the end of this number, so I know that 5 is a factor, but 5 times what will give me 125? Check it out, right? So we didn't do anything with this 5 because that's prime. Ooh, we got to stop right there, right? However, 125, that's a composite number. So there's different factors inside of it, not just one in itself. Correct, my friends? Yeah, correct. So we have 5 times 25 will give us 125, correct? But notice we got another prime number over there. That 5 is in the lowest terms I can make it. So 5 is here to stay. But check out 25. Is 25 a prime or a composite number? Check it out. So we know, my friends, that we took this big old composite number, 625, and we started breaking it apart to get different factors so that we could get this number in the smallest terms that I could possibly write it in, correct? So we broke it down. We knew that 125 times 5, equals 625. But then I was trying to figure out, okay, what can I multiply together to get 125? And we know that, hey, 5 is a factor of that, but 25 was also a factor, my friends. And since I circled this, that was my stop sign. You can't break down a prime number any more than it's in its prime format, right, my friends? But check out 25. You know that there's two numbers that can be multiplied together in order to get 25, and that number is 5, my friends. So I broke it down. Now you'll notice we have a 5, a 5, a 5, a 5. That, my friends, is how we were able to take this big old composite number, 625, and break it into like the smallest little prime pieces that it can be, all right? So prime factorization, we start with a composite number, we break it down, break it down, break it down, break it down as far as we can until we can get everything in its prime formula, right? The prime building blocks to a bigger composite number, if you will, my friends. Okay, so maybe you watched all this and you're like, hey, Mrs. Schlecht, that's all well and good, but I'm like a big time smart 6th grader. That's not new to me. And I thought we were talking about exponents, Mrs. Schlecht. Yes, we're talking about exponents, and now I want to show you how we get that. Okay, do you notice that 5 is circled, 5 is circled, 5 is circled, and 5 is circled, right? How many 5s can I actually multiply together in order to get 625? All right, so all I did, my friends, was I just took the information I was able to get from my factor tree and I just wrote it out as a multiplication sentence, right? So the reason I did not write 125 or the reason I did not write 25 is because those are those composite numbers, my friends, that I broke apart, right? So remember, these two 5s, when I multiply them together, gives me 25, correct? And when I multiply these two 5s with this 5, that gives me 125, okay? So same sort of idea over here, my friends. 5 times 5, that's 25. Check that out. Look at that. And then 25 times 5 is 125. Oh, check that out. And then 125 times 5 is 625. All right, so now we're going to get to the exponent portion of our lives, my friends. Notice this is a 5, this is a 5, this is a 5, this is a 5. So all exponents do is they represent repeated addition with the same number. So a 5 is being multiplied by a 5, which is then being multiplied by a 5, which is then being multiplied by a 5. So since I am multiplying the same number by itself over and over and over and over again, I can use exponents to represent this. So maybe you're wondering, like, how in the world can you represent that using exponents? That's a great question. So 5, the number that's repeating, the number that I'm multiplying a whole bunch of times, that becomes our base, the base, okay? So in this example, in this number that we wrote here, the base is 5, again, because that is the number that I am multiplying by itself. Now you'll notice that there's a little tiny 4 right here, my friends, and that beautiful 4 is our exponent. That's what that little thing is. Now what that beautiful exponent tells you, my friends, is how many times I am multiplying 5 by itself, okay? So I noticed after I did my factor tree and got my prime factorization, right? I noticed that I could multiply 4 5s together and I'd get 625. So that's how I'm able to represent that as an exponent, correct? So 625 is the same as 5 times 5 times 5 times 5, which is equivalent or equal to 5 to the 4th power. All right, but before we move on, I need to tell you something super duper duper uber important. You ready? Okay, so we just said, my friends, that 5 to the 4th power meant 5 times 5 times 5 times 5, right? 5 to the 4th power is not 20, okay? We're not doing 5 times 4, that's 20. No, you guys have been multiplying for like years at this point, and you've never seen multiplication like this to get 20, right? That's because that's not a thing, thing, that's not a thing, okay? So please, 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 please remember that when you have a base, which in this case is 5, and you have that little tiny 4, which is the exponent, you are not multiplying these two numbers together. You are multiplying the base by itself that many times. Let's check out page 126, number 9. All right, a couple of things I want you to notice about number 9 before we get going. One, I know that there's fractions. However, all those rules that we just talked about, still the same, okay? So please don't let little fractions scare you off. It's the same stuff, okay? Second, if you remember, last time the number that we kept seeing over and over again was 5, right? And that became our base. Now check this out, my friends. What number do we see repeating over and over and over again? 3/8, right? So 3/8 is going to become my base. Again, 3/8 became my base because that is the number that I am multiplying by itself, correct? 3/8 times 3/8 times 3/8. So the base of my exponent is going to be 3/8. But what's my exponent going to be? How many times am I multiplying 3/8 by 3/8? Ta-da! 3 times. So my friends, we could represent 3/8 times 3/8 times 3/8 as an exponent, 3/8 to the 3rd power. We might also call this 3/8 cubed. All right, so the last problem I want to work with you guys on is page 126, number 4. Now, my friends, my beautiful friends, I think we've kind of talked about this sort of stuff before, but if we were in the classroom, we'd have a lot more time to really dive deep into all the fun math, right? But, since we're in this setting, sometimes we got to kind of get going, right? So this next thing I'm going to talk to you about might sound super duper big, okay? Because it kind of sort of is. But if you want to find out more information, if you want to talk more about this relationship, office hours or Google Meet, email me. Oh, I will totally love to talk to you more so about this next thing we're going to talk about. But again, given our current situation, my friends, got to kind of speed it up. So if you need more help, let me know. All right, so number 4 is kind of one of those bigger questions, but the main thing it's asking you, my friends, is if you have 2 and 5/10 and you multiply it by 10 to the 0 power, that's a little tiny 0, but it's a 0. What's that equal to? And so for this whole part, can we just ignore this? Let's just erase that, okay? I want to talk about 0 as an exponent. Right, so first we're going to go back in time, back in time, back in time to that first problem that we did, which again was in our key concepts box. And we discovered that the number 625 could be written as 5 to the 4th power. We also know that 5 to the 4th power, what it actually means is 5 times 5 times 5 times 5. So remember, my friends, all of this is equivalent. They're all equal to each other. 625 is the same as 5 to the 4th power, is the same as 5 times 5 times 5 times 5. Another way that we could think about this, though, is how many times am I multiplying the number 1 by 5 times 5 times 5 times 5? We could also rewrite it like this. Now, you know, my wonderful friends, that anytime you multiply 1 by a number, it doesn't change, right? That's the identity property of 1. Once you multiply something by 1, it doesn't do anything. It just stays the same. So we're going to use that rule to help us figure out this piece, okay? So when I have 5 to the 4th power, that's really like saying, hey, I'm taking the number 1 and then I'm multiplying it by 5 4 different times, right? And that gave me 625. So let's see, what if I only had 3 5s? How would I write that? Using that 1. So you could just write it like this: 5 cubed, or 5 to the 3rd power, is the same as 1 times 5 times 5 times 5, and that equals actually 125. But what happens if I don't have any exponents that I want to multiply by? All right, so now I have 5 to the 0 power. If we follow this pattern, we know that this actually means 1. Ooh, but how many 5s am I multiplying it by? 0. So I'm just left with 1. So here's a really interesting, cool kind of thing, my friends. Every time that you have an exponent that's a 0, do you know what that's equal to? It's just equal to 1. So if we look back at our original problem, 10 to the 0 power is still just equal to 1, because this is not me doing 1 times 10 times 10. No, I just do 1 times, there's nothing to multiply it by. So remember, whenever you see 0 as your exponent, that is always equal to 1. So real quick, just like we discovered that anything to the 0 power is equal to 1, anything raised to the first power is itself, because we're just multiplying one group of it, correct? So when I had 5 to the 0 power, we know that's just 1, because that was going to be like 1 times, and then we got cut off. There's nothing else there. It's just 1, right? But then over here, and this is a little tiny 1 over there, right? When I'm raising 5 to the first power, I only have 1 5, right? So I'm still multiplying by 1, but what's 1 times 5? Well, that's just 5. Okay, so here are some 2 big exponent rules, patterns, whatever you want to call them, okay? If your exponent is 0, the answer is always, always, always 1, okay? If your exponent is the numero 1, okay, if your exponent is 1, then whatever your base is, that's the answer. All right, my friends. So again, that was just a really quick run through over exponents, which goes with lesson 3-1 in your book. And like always, if you have any other questions, please let me know.